Hello, in this video I'm going to say a bit about transformers. This is a piece of equipment which is now just essential to everyday life. They get used in the national grid where we're distributing electricity around the country. They're essential for that. We use them every day. They're in our mobile phone chargers, they're in our laptop chargers, tablet chargers, things like that. And the reason they're so important is depending on what it is we're trying to achieve with electricity. We want to be able to change our voltages around. Sometimes we want very high voltage, sometimes we want very low voltage, and transformers are what allow us to change our voltage. We can step up voltage, we can step down voltage. So let's take power distribution as an example. Power stations, we might get 25 kilovolts as the potential difference. This is the EMF that's coming out of our power station. This is the difference between the out cable and the in cable in the power station. We're going to have, say, 25,000 volts difference between these two cables. But that's not high enough for when we're wanting to distribute energy, distribute our electricity efficiently around the national grid. So we'll have a transformer which will then step up the voltage up to, say, 400 kilovolts. This means we're dropping the current down. If we can distribute at low current, then we're going to get less energy loss when we're distributing around the network. But of course, we don't want to be pumping 400 kilovolts into industry or the home. So we need to step it back down again, step it back down for what we need at industry, like 30,000 or 10,000, depending on what sort of industry it is. And then we can step it back down again to the 230 volts that we have coming into our homes. But even then, the stuff that we plug in at home isn't all operating at 230 volts. We might want to step down to, say, 5 volts for our mobile phone charger. So the ability to change voltage by using transformers is ridiculously useful. It makes all of our electricity use so much more efficient and so much less dangerous as well, because we can change our electricity supply to match our needs. Right. So what actually is going on in a transformer then? Well, the basic setup of a transformer design is you'll get, these were the original ones that were built. You get this iron core, and we'll have 2 coils of wire which are wound around this iron core. So we've got our primary coil on one side, and then we've got our secondary coil, which will have a different number of windings on it on the other side. So just to make it easier, I'll just draw a very few number of windings, but these might be hundreds of windings on here depending on what it is you're trying to do. And then we're bringing into play our principle of electromagnetic induction. So we want to get a changing magnetic field. This is what we want here, in order to induce an EMF and essentially induce a magnetic field inside the iron core. So you remember what we had here for inducing EMF. So our induced EMF, this depends upon our rate of change of magnetic flux linkage. So we need to be changing something. Well, we're not changing the number of windings. We need to be changing something in our B field, because we're also not going to be changing. Remember, our magnetic flux was BA cos theta. We're not spinning anything here. We're not changing the area inside these coils. So we need to change something in our B field. And the way we're doing this, the way we're changing the magnetic field, is by having alternating current in these in the primary coil. So if we've got alternating current in the primary coil, that means we're going to have a changing magnetic field around this coil, because the current's changing direction all the time. It's changing direction and magnitude. So the magnitude and direction of the magnetic field around the wire is going to be changing. So from the point of view then of the iron core, the iron core is sitting there as a conductor, and it's got a changing magnetic field. So that changing magnetic field is then going to induce an EMF inside the iron core, which is you're going to start getting electrons moving around. So we've now got current flow inside the iron core, which we want to minimize. I'll get back to that in a minute. But this is then, we've now got a magnetic field which is changing inside the iron core. So just as we've passed on from the primary coil into the iron core, we're now going to pass from the iron core into the secondary coil. That changing magnetic field in the iron core is then going to produce an EMF in the secondary coil, which is then going to create an alternating current in the secondary coil. So the alternating current part of all of this is essential. You can't do this with direct current, because you need the changing current to get the changing magnetic field to then get electromagnetic induction operating inside the iron core, and then again inside the secondary coil. So we've got this flow here, this step-by-step change in the primary coil gives change in the iron core, gives change in the secondary coil. Right. How do we then make this more efficient? Well, there's two things we want in the iron core. We want it to be soft iron, by which we mean not as in physically soft. This isn't some spongy metal. It's still hard. It's still iron hard. But we want an iron core which can magnetize and demagnetize. Essentially, we want an electromagnet here. We don't want an iron core which is going to become permanently magnetized, because it's then going to affect the electromagnetic induction. So we want soft iron, which means that when the transformer is operating, the iron becomes magnetized and it can transmit the effects of the electromagnetic induction. But then when we turn off the AC in the primary, it then demagnetizes and it doesn't stop working the next time we put the current back on again. So that's what we mean by soft in the iron core. The other thing is the iron cores are then laminated. So this means they're not one solid block of iron, they're actually layers of iron. So if you take this side on, I'll draw it a bit square just because it's easier to do. And we've got our hole there, so that's just sort of angling this a bit. Then the iron core is made up of thin strips. So you've got a narrow sort of thin strip and then another one. Oops, that's not very well drawn. But we're stacking all these up. So when you get the depth on it, remember we're wrapping the coil around this, you've got all of these layers, separate layers of iron, which are all stuck together in order to create the depth of the iron core. So this is what we mean by laminated. The reason people do this is it reduces the amount of current that flows inside the iron core. We don't want a lot of current because that means it's going to start heating up. We're going to get energy losses and our transformer is going to be far less efficient. So we want to do what we can to increase the resistance of the iron core in order to, if the resistance is up, the current will be down, which means our energy loss will be reduced. So this laminated core reduces what they call eddy currents. You get these eddy currents in there, and the lamination reduces that. So we got this chain of electromagnetic induction, and we know that the induced EMF is proportional to the rate of change of flux linkage. So the more coils that we've got on the secondary coil, the higher the EMF we're going to induce, because the more coils, this is the N in our magnetic flux linkage. So in this case, I've got, especially if I just add a few more here on the primary, we've got fewer turns on the secondary coil than on the primary. So we're going to have a lower EMF. This is going to be a step down transformer because of this N here in our Faraday's law. Although in this case, of course, this is Faraday's law plus Lenz's law because it's written with an equation. Faraday's law, remember, is just the proportionality. And then when we add in Lenz's law, we then get the equals minus times the rate of change of flux linkage. So just keep that in mind all the time. But still, this N here, the number of turns on the coil, that's determining whether we've got a step up or step down transformer. So we can then get an equation where we say, well, the number of turns on the secondary coil divided by the number of turns on the primary coil is equal to the voltage of the secondary coil divided by the voltage of the primary coil. Because as we've seen here, the induced EMF, our V secondary, is proportional to the number of turns on the secondary coil. That's what we've got going on here. So this equation, it makes sense in terms of Faraday's law. We can see where this is coming from. Of course, we can extend this then into talking about current as well. Say we had a transformer that was 100% efficient, then that means power in is equal to power out. So our power in, V primary times current primary, that's power, and it volts times amps, is going to be equal to V secondary times current in the secondary. So we've got this as well, can also allow us, for a 100% efficient transformer, allow us to work out the current in the secondary coil. So we've got these simple equations that we can use. And you can see here, I mean, it's just this straight ratio here. If we want to step down to 5 volts, then we say, okay, well, we want to go down to 5 volts from 230. So if we've got, say, 100 turns on the primary coil, well, it's easy to work out what number of turns we're going to need on the secondary coil. So yeah, obviously these transformers, they come in a great array of sizes and setups, and there's been great engineering advances in making these things more efficient and such like. And of course, a transformer in a power station, which is stepping from 25,000 volts to 400,000 volts, is going to look considerably different to the tiny little transformers that you've got in your mobile phone chargers. But the principle is the same thing. We're using electromagnetic induction in order to change the voltage of our supply. So yeah, there you go. They're quite simple. They're nice questions that come up in exams because we've got simple equations. Make sure you can see this link between the formula here and what we've done in Faraday's law, and that you can understand the basic principle of how we're getting this chain of electromagnetic induction going from one coil to the other. But yeah, these are ridiculously useful bits of equipment. I mean, the mind boggles. We just wouldn't have a society even vaguely like what we've got at the moment without transformers. Truly, truly revolutionary.